Hello. So let's start. Okay, let me share the screen. So, oh yeah, by the way, I need to send you the material. Here. Yeah, it's landed into the chat. So let's start now. Today we will speak about morphology mostly, but not only that topic. I think we will cover a couple of other topics as well. So first, all the imports with all the libraries, and started. First, let's speak a bit about color spaces. Color spaces, in fact, is a big topic, but what we need today is that our color spaces are three-dimensional ones. As I said before, for example, in the human's eye, we have three types of color-sensitive cells. Well, for day vision, and that's a fundamental reason for having three degrees of freedom in color space. And these three dimensions could be parameterized in different ways. So one way we already seen is RGB, and it is related to our cells, and it is the best for describing emitting sources of light. They are described in RGB. That's why our screens work in RGB, and we store it in the ways that are compatible with our displays, since they emit light. Another thing is hue, saturation, and value, and hue, saturation, and lightness. They are connected, but we'll mostly speak about hue, saturation, and value. So this parameterization is a circled one. So the hue stands for color, full color representation. Then saturation stands for kind of being more being white or being colored. This is how it's done, yeah. And value represents some kind of intensivity, but not generally. Yeah, it's connected with lightness. They correspond to each other, but parameterized differently. So
Vladislav,
Uh-huh.
I understand then the difference between saturation and value. So hue is color, it's okay. But if the saturation is between dark and white, then and value also the level of intensity, then what's the difference? How to feel it?
It's not very good microphone, but I will try to figure out. So the difference between the colored point and the white color is saturation, and the way of what value corresponds to the if we use some analogy, so it's corresponding to the intensity of light that we shine that the object shines, for example, or that we put into object. Is it more clear?
In the picture, I see that the rectangles show only h equal to 1. So can you show similar for HSV equal to, for example, half, 0.1 or 0.8? Then it will be much better to understand, much easier to understand.
Oh, you mean this picture?
Yes, I mean this picture. It's only for HSV equal to 1, right?
Yeah.
Yeah, would be great to see a similar picture for HSV equal to half.
Okay, I see. Well, in fact, it's no, it's yeah, it's a saturation one. For saturation less than 1, we'll have what we'll have. Yeah, it's a projection. It's a okay, for hue and value. Yeah, this is this saturation of 1. So all the picture will get darker. In fact, this is yeah. Speaking about the color. So I mean interactive choosing of color is supported, for example, by macOS, but okay, I won't. I don't think that I could make it dynamically here. Well, the picture will get lighter and lighter. So we will go to, if we decrease saturation, we just will, this is kind of the border of this cylinder. And if we decrease saturation, we will go to closer to white light.
I see now. I understand. It's better. So it's not value is the difference between dark and intense, and value is saturation is the difference between intense white and intense specific color, right? Like
kind of, yeah. And the value is connected with magnitude of light that you put on the object. So, for example, if you are in the dark room, like completely dark, you see nothing, and it doesn't depend on what you have. For example, we have several cubes, red, green, blue, cyan, magenta, everything, and all of them are dark. Like they are black for us because we have. Yeah, and the value is intensity of our illumination. Yeah, and yeah, hue is for color. This is okay, and saturation is what we see when we get the same color more and more, not intense, but yeah, the saturation is difference between completely light object and yeah, colored in some way. So the formulas for changing this space from this representation into RGB is not linear, and yeah, I think boom. Yeah. Not so easy. Okay. So it's not connected linearly with RGB because we have this circled hue, and it's saturation, which is kind of circle too. So I mean, different colors intersect each other, and from the point of view of RGB, this would look like going more green, more blue, more red, and so on. That's why it's not a linear one. And the OpenCV and other packages, for example, here we use scikit-image, which is based on Pillow, Python image library. They have RGB to HSV function with all these nonlinear transformations. And here we can see different, this is an original image, and this is hue and value channels. So we have, when we translate from one color space to another color space, there are different color spaces, not only two. I think there are a dozen of them or something about that. They're used for different purposes, but RGB, HSV, and SMIC is the most used in practice. So the last one, SMIC, is used for printing. This is because RGB is connected. So I think let's I think look at it. Yeah, and this is SMIC color scheme. This is for reflecting sources, for reflecting objects. This color scheme is used for printing. When we print something, we not emit light directly, but we make it of this, it's a secondary light. Yeah, that's why we need different colors to describe the same things. So for example, to get the red, we have to mix magenta and yellow, and here, if we mix any pair, we will end up with basic colors for RGB. That's how this color scheme is made. So it's used in printers usually. Well, and by the way, if you open up the your colored printer, you will see four inks. Three of them will be magenta, yellow, and cyan, and the last one will be black. Because if we mix up all three these types of inks, we will have something kind of dirty, and the black color should be separated for kind of technical reasons, not physical reasons. But for image processing, the HSV scheme is very well. It fits very well. Then What can we do with this thing is we could segment the image with the same ways that we did before for RGB. The last time we made binarization, and we performed some actions with histogram, and one of the actions is binarization, and we could binarize it by hue. So one group of hues goes one way and another goes other way, and this is what we got. So for example, we have segmented most parts of this object, yeah, and later we will see how could we segment all the object from its background using such a simple method. And before neural networks, it is usually done this way. So we perform some transformation, then we apply some thresholding, and then we get some segmentation, some lines. We detect some lines and so on. Let's look how it's used. Yeah, that's another way. And by the way, speaking about colors and color schemes, here is all the flags from OpenCV for translating from one color space to another color space. For example, we could see here what we what we used the last time. For example, RGBA, but we haven't used A, but that's not the point, to BGR. So the already common things for us, but here is a list, and you can see that OpenCV has many translations between different color schemes. In fact, many different color schemes exist. Yeah, this is an online demo, but we won't trigger it because it requires a web camera, which I use for this recording. So we will skip it for now, and we'll go for images binarization. Yeah, this is original image of a man filming something, and our goal here is to segment the human from this photography, from this image. And this is what we get after we threshold our histogram. What are we doing? We apply Otsu filter. That's another type of filtering that we will consider, and then we have a histogram of linear, some simple one-dimensional feature, which we threshold, and that's how we get the binary thresholding. And speaking about thresholding, for example, for optical character recognition, this is a very popular task nowadays. By the way, nowadays it's of course solved with the neural networks, but before that, people used to apply some thresholding. And here we see different methods of thresholding applied to the same original image. And usually the pipeline for, in fact, there are many of different types of thresholding algorithms. So this is the algorithm that creates some linear feature that we could threshold. Yeah, and that's to solve some particular practical task. researchers or maybe engineers usually looked at the image with different approaches applied to this image, and by hand they choose the best one and hard-coded it into the pipeline. So the pipeline, the resulting pipeline is not very stable to some changes and so on. And that's a starting point of creating kind of yes, some statistical algorithms which ended up in convolutional neural networks. That's the starting point of our machine learning course, for example. And here we see why did it happen? Because simple algorithms and simple rules that could describe the image or create some value, some simple value, they're not suitable for all the cases of environmental, for all environmental cases, for example. So yeah, another way to get some shapes from an image is so-called morphology. And here, what we get is we visualize so-called structuring element. This is a pattern that we apply to image. We will look more at it later, but for now, let's look at some examples. Here we have different kernels with different shapes. So, for example, cross-shaped kernel and elliptical kernel, but elliptical kernel is binarized. That's why we see it as a cross with different width of its crossing elements. But in fact, if we take an ellipse and we count how many points went to one, well, kind of binarize it, yeah, then we end up with this structuring element. And what we do next is, in fact, we make some kind of convolution on this structuring element. So that's a kernel for convolution. You could think of it in this way. And what we make in the following step is we apply this structure, so-called structuring element, to some image. And here, for example, we have and this is called morphological operations. This is an original image. And the first operation is dilation. And dilation performs the following thing. It places structuring element to every pixel that we... morphology is made on binary images, so we binarize them somehow, and then we apply the structuring element. So we put it to every point, and we get resulting to every point of original image, and we get resulting image by applying structural element to every point, every white point in this case, of original image. Yeah, when we apply it kind of in to every white pixel, we end up with dilated image where every white element becomes thicker. Yeah, and the mirroring operation of dilation is called erosion. And here erosion is applied. So we do the opposite thing. We apply kind of negative structuring element to black pixel. Yeah. In fact, it's defined with this formula. Yeah. We just take minimum of some neighborhood of each pixel. So in fact, it is connected with convolutions. That's why it's connected with convolutions. But the main thing here is that getting structural element, we could make every white pixel either thicker or thinner. Not pixel, but some shape. Some shape on the image, we could make it one way or another. And the next thing that we could do with these two is we could combine them. So, for example, if we combine, first we apply erosion, and then we apply dilation. This combination, erosing then dilating, so erosing is biggering, erosion is making everything thinner, and dilation is making thicker. So this operation is called opening. And the opening operation could, with opening operation, we could get rid of some noise on the image. So first we apply erosion, and these little points disappear, but bigger elements of this on this image don't disappear, and that's why when we delete it back, we end up with the same image and with the same shape, but we don't see any small noise on the image. Is it clear why do we end up with this effect? So we make everything thinner and thicker back. Mm-hmm.
The kernel is bigger than the noise size, right?
Yeah, the size of the kernel is depending on what of how big should be shape to become noise. Yeah, and the form of the kernel is corresponding to the dimensionality, or maybe if you apply, for example, you could create opening for only one dimension. So, for example, horizontal dimension, or you could apply it to diagonal element, and you will get rid of everything that is not thick in some vector. So by some vector, this is how it's done. So the two main points is size of kernel and shape of kernel. And here in the illustration, we have different types of kernels. So we could make our kernel just rectangular. So it would be a rectangle, yeah. Or maybe we could apply cross, or we could apply maybe one-sided rectangular, and so on. Very different types of operations. And another thing, kind of mirroring opening, is making the same things, but in the opposite order. First, we delete everything, so we make everything thicker, and then we erode it back. So this is a way to get rid of this black noise in the shapes that we are interested in. This is how morphology works, and it's very it's very nice as an element of other operations. So lately we will chain those dilation, erosions, opening, closing, and so on, and we end up with image processing algorithms that could get some not obvious things from the image by these simple operations only. Yeah. Even with this four things like erosion, dilation, opening, and closing, we could do more interesting thing. For example, we could subtract dilation and erosion and get so-called morphological gradient. So this is in fact the border points of each element. Yeah, and this is the way to get yeah, kind of a gradient line, and it depends on the kernel as well. So depending on the kernel size, we'll get different things. And if we apply it to this noisy image, for example, we will get these points too, and these points too as well. Yeah. For example, we could subtract them from original image or make something on it and so on. Another two operations is subtraction opening from source image, and this is called white hat. This is elements that are that is kind of stable on the image, so they we make disappear something that is stable for opening, and kind of mirroring operation is called black hat, and in this way we first create closing of our image, and then we subtract source image from that, and what we get is kind of this. Yeah. It means that this is parts of image. Oh, it's yeah. How could we describe it? Is I don't know. I think we could just use the formula. So yeah, for now it's okay. And let's apply these morphological transforms to more complex image like this. Here we have some shapes and so on. Yeah. And first is erosion. We apply it to our structure, to our image. And as I said, since we use kernels, we could apply it to as a mask, as a convolution. Yeah, and this is what we end up with. So we get rid of this white border, and we our two circles became a balloon. Yeah, so they joined each other and became one shape. If we apply dilation to our more complex image, then we make everything white becomes bigger. Yeah, that's why these circles just became bigger, and this became bigger too. Then if we apply opening, we get rid of white noise. Yeah. Okay. We get rid of some white noise, which is less than our kernel size. And we see that here the border was thin, and that's why we get rid of it. And here the border became kind of equally thick. So in this case, we see that it's first thinner, then becomes thicker. But here the size is the same, the thickness is the same, because we applied opening on that. And also, yeah, we get rid of these white points. Yeah, this is standard example from OpenCV, and the closing works as this. So if, for example, why closing could be handful, because if we apply some noise here, then closing closing helps us to denoise this image. Yeah, all the other structural elements, as you see, not structural, but all other shapes remained the same, but this noise just disappeared because we applied closing on that. So we get rid of kind of black dots. Yeah. And this is a closing, standard closing from OpenCV. Yeah. Then morphological gradient we already seen. And if we apply top hat here, this is what we end up with. So this is why it is called white top hat. So we retrieve all the white kind of white noise, yeah, because this upper part is not considered as a noise because of opening, because we defined it as it is bigger than structural element, and that's why we don't see it in top hat. And if we subtract, for example, this white top hat from original image, we will get rid of this white noise too. Yeah. So how could we apply it in practice? We get original image with some shapes here, and then we apply top hat, and we see all the small noise on the image, and then we subtract it. We subtract original image minus result, yeah, and then we see kind of denoised image without these small parts. Yeah, this is how it's done in practice. So if you if you know the structure of your noising reasons, or maybe some type of it, yeah, you could predict what operation should you do with morphologies first, and then what coefficients should you use when subtracting these elements. So you could get some structural element, you could get size of the structural element, apply some morphology, and then subtract it with different coefficients. And that's how you will suppress noises on your image. In fact, morphology is one of the greatest thing in classical computer vision. It enables us very, very different image transformation, as we will see below. Yeah. And as I said before, we usually apply all these operations in chain. So we could make, for example, white hat subtraction, then closing on that, then something else, different chains of morphological transforms, and also morphological transforms are applied not to original image, but to some processed image, some binarized image, for example. Let's return to our original man with this photo camera or video camera, yeah. And let's imagine that we have applied some morphology operation here, and the only main man remained here. So let's make it, for example, yeah. Let's copy this thing and let's go here. Let's go here. This is our binary image, and what could you suggest to for this only this person to remain? Yeah, we have only mask. Any ideas? What should we apply out of this?
Can you repeat what is the task? What should we?
So we want only man to remain. So we want to filter this camera, this background, and get mask for the man.
Open, close.
Yeah, for example, we could apply so first I would invert the image, yeah, and then I would apply opening on that. Yeah, I haven't. Yeah, I haven't.
Kernel size, right?
Selenium,
it's kernel size, right?
Yeah.
Kernel.
It's a kernel. Let's define it. Yeah, and here we see that everything or we could see 1 minus open man. Yeah, and this is how we could get only man. Yeah, I think that our kernel was not big enough. For example, let's make it 7. Yeah, so the only man now is present on this binary mask. We will see what could we do with this mask later on. Okay, let's move on. For now, I think yeah, that's a kind of more practical illustration of what we do. So, okay, the next thing is skeletonization. Our goal here is to end up with some shape that is kind of skeleton. In fact, it should be all the nodes, all the pixels should be connected as they were on original image, but we should get this type of thing. We do that by we do that iteratively, and we kind of subtract pixels from borders of an image, and then we those pixels remain that have more neighbors. Yeah, and step by step we end up with this skeletonization. Then also we why do we need skeletonization? To get some objects, some like large object on image. And for example, after this skeletonization, we could apply our morphology transforms and get rid of smaller elements here, for example, and only this will remain. And another thing, yeah, yeah, this is the picture of borders and skeletons, but yeah, here we see not the image skeletonized partly. So we didn't subtract all the pixels from the main part, but some parts remained. So we stopped at some point, and that's another way to get more to get some semantically valuable things from the image. This is one part of pipeline. And what next can we do with such morphology transformed image or skeletonized image? The next thing is we could create a convex hull out of it. And this is a convex hull for the horse, but we could apply, for example, this convex hull to our for example, let's call it man mask, and this would be this thing, yeah. And for example, if we yeah, man mask, if we now apply convex hull on that mask, this is a mask, yeah, for our man. So finally, we solved the task of finding man on image. This is how is joked in mathematics. For example, when the task is to find the x, the answer is here's the x, and yeah, here's the man. But it's not an obvious how to do that programmatically, how to do that without, for example, training thousands and thousands iterations on some neural network. So we could do that without such complex stuff. Yeah, but convex hull is not very it's not very robust, because even 1 point could make us fail. That's why we should apply previous methods, just like skeletonizing. For example, if we skeletonize it, then we, for example, apply closing to this image, then we get rid of some small noise, then we will return to original image and mark all the pixels that that is from this object, and then convex hull would work well for us. Yeah, and yeah, that's the resulting of our horse. And another nice image processing algorithm is called Kenny edge detector. Edges on the image is a very fundamental thing, and there are many ways to find such borders, edges. Yeah, and there are these types of things are called in two ways: ridges and edges. Edges is this thing, and this thing is in fact ridge, because for example, let's oh, that's from NLP. Yeah. No, that's not the case. Okay. So when we have, for example, kind of once, then we go to 0 and we got 0 zeros. That's the edge. And when we have zeros, then ones, then zeros again. That's the ridge. And to detect both of them, we could use edge gradient by defined by Kenny. Yeah, and this is how we compute that. And based on these equations, we could calculate such a formula for each point. So we calculated for some for direction x, for direction y, and then we could threshold it. So at this point, we create such a rule of max val and min val. So for each point, we calculate gradient value, and this is just the same thresholding, simple one-dimensional rule for solutions, and the rule for the following processing is as follows. First, if some pixel is above max val, then we we think of it as about edge. And if something is connected with this, but it is not below mean val, then it's an edge too. So if something is below minimum value, it is definitely not an edge or ridge or something. So it is not a border. But if something is above max val, it is definitely a border. And in between, only it is border only in case when it is connected with something above the max val. And this algorithm is kind of simple, but it is very powerful. In fact, it enables us to detect edges and then to perform such transformations. Then we get the source from this transform to our later morphology, skeletonization, connectivity components, and so on. Yeah, and if we apply, for example, this transform to some image, then we get this thing. And by the way, before calculating gradients, we should apply Gaussian blur to the image, because we need to detect not so many edges, because for example, this will have some gradients too. And you see, t-shirt of this man has many different edges. And if we want to get more robust edges, we have to make this kernel bigger, because on bigger kernel, small edges gets blurred, and more stable edges exist still. And then we apply this transform with double thresholding. This is how Kenny filter or Kenny edge detector works. Yeah, and this is a basis for applying morphology filters, which we spoken above. So if we apply right morphology transform, we could get rid of this small noise and of this, and only men remain. And this is, for example, the way to to make our stuff. For example, we could want to detect the ball on the field, and this could be done relatively robust with these methods. Yeah, this is how Gaussian blurring affects Kenny. On small Gaussian, we see many noisy things, but when we apply bigger kernel for initial Gaussian blur, then we see clearly right borders. Yeah, and the last method that I wanted to discuss today, we won't speak about half transform. It's a more complex thing. We will speak about it on the separate lecture and seminar. For now, let's look at another way to segment things, and it's a water shard it's called a water shard. The first thing is we select some points that are that represent different objects on the image, for example. And this example, we try to segment, for example, two coins that lay on each other, and we have an image of them. And we want to separate one from another. And we define centers with some way. For example, we could create, in this case, we could apply dilation, erosion, all the morphologies, and end up with a center, or we could apply skeletonization and end up with this line containing centers, and set it as a starting point. And then the metaphor here is just these points are the bottoms of our of some landscape, yeah. And then we put water in it, and water gets upper and upper and upper, and at some point they meet each other, and that's how this border is created. For example, yeah, it is based on distances from the source, and we, in fact, we apply BFS on this, and that's how we get these two points. Yeah, I think that's the last method for today. All of these are just some bricks in bigger algorithms that could process images in more advanced ways. And even with this simple tool, we could assemble some complex pipeline that handles some better defined environments than nowadays neural networks can do, but still it's a powerful instrument. And the main point is that these instruments usually work faster than some heavy neural networks based solutions. Yeah. And it is nice for pre-processing and subtracting simple artifacts from images. Yeah. So that's all for today. Okay. Okay, thank you. Bye-bye.